So, basically what happens whenever degeneracy occurs, you are moving from one degenerate basic feasible solution to the other degenerate basic feasible solution. If you see here, the procedure is moving from one degenerate BFS to the another without changing the Z value, that is the problem. So, it may happen that whenever I have started from a current degenerate basis B, after n iteration I may return back to the again to the degenerate basis B with no change in the objective function, that is the Z value. This implies that next n iterations will again produce the same basis B. So, basically there is no improvement and you are just moving from one place to another, and ultimately you are coming back to the initial point again, and such repetition we call it as cycling. So, there are methods for basically generating a sequence of basic feasible solution which in spite of degeneracy effect will produce the optimal basic feasible solution. So, basically we are saying that whenever degeneracy occurs, then usually if you try to follow the normal method, in that case there will be no improvement in the objective function. But there are several methods available for degeneracy reduction like Chance, Danzig, Orden and Wolf. Various methods are available, but we will discuss only one of them. Now, situations in degeneracy. Basically, two types of situations may occur in the degeneracy. Degeneracy occurring at the initial stage itself. That is, it is detected when at least one of the requirement vector vanishes. That is, corresponding basic variable value is 0. So, initially whenever I have formed, I am finding that one of the basic variable is 0 in the initial basis. To obtain the basic solution, optimal solution in this case, you proceed normally, that is as usual, until the optimality condition is obtained. You do not have to do anything extra. That is, whenever at the initial stage you are finding this one, then proceed as usual and you will obtain the required solution. But the second one is degeneracy at subsequent iteration. It may happen that corresponding to the key column, that is where value of Zj minus Cj is most negative, two or more rows sum to be equal prospective for selection as a key row. That is, if you remember in the earlier examples, if I take a table, whenever I am taking a table, you are calculating the ratios. Now, if it may happen that the value of these ratios are same in more than one entry, that is because of the reason xbr by yrj values are equal. So, degeneracy occurs number 1 if you can find it initially, where the value of the basic variable is 0. Another one comes whenever you are calculating the xbr by yrj ratio, that value is same in more than one element on that ratio column, then also the degeneracy occurs. There is a theorem with respect to this. When there is a tie in selecting a departing vector, there is a tie. So, tie will occur whenever the values of the ratio are same. The next solution is bound to degenerate. So, whenever there will be a tie in selecting a depart variable, then in the next generation their solution will be degenerate. So, I have to find out the method by which I can remove this degeneracy, so that degeneracy does not occur. So, if I have degeneracy as we have told earlier, then there will be no improvement in the solution, you will go on doing iterations. Therefore, whenever the ratio of one or more than one elements of the ratio column are same, degeneracy occurs. So now let's see how we can improve degeneracy or eliminate, overcome degeneracy. Chance perturbation method to overcome degeneracy. When there is a tie in the departing vector, number 1, rename the column vectors of A in such a way that initial basis B consists of first m columns of vectors Aj of A, or in other sense, if I consider this thing, here your basis variables are Z and W. So now you consider this as Z. Basically we are saying you consider first column as Z and this W you consider as this one. So basically here we want to say is that whenever there is a tie, you consider the first column as the first element of the basis and the second column for the second one of the basis, which I have written here, that rename the column vectors of A in such a way that initial basis B consists of first m columns of vectors Aj of A. Now let AK be the entering vector. I am giving the example of this. Here your y is the entering vector here, which I am saying as AK. Compute minimum of yi1 by yik, where yik greater than 0. Minimum of yi1 and yik. So please note that here if this is the case, then yi1 by yik. yi1, yik, whenever you are going to calculate, there you will consider this as the first column for the basis variable, this as the second column for the basis variable. So now you compute minimum of yi1 by yik, where yik greater than 0 for all I, for which your tie occurred, that is minimum of xbi by yik k greater than 0 occurred. If minimum of yi1 by yik greater than 0 for all I occurs for only and one value of I, that is whenever again you are finding out the minimum, and after finding the minimum, if I can find a value of I for which is unique, where the value is minimum, which is say I equals S, then you will tell AS will be the departing vector. That is for which I the minimum occurred by changing these columns of the columns of the simplex table, that will be the departing vector. And if this minimum occurs for more than one value of I, then I have to go to the next step. That is still there is a tie. So I have to go to the next step. Step 3 is compute minimum yi2 by yik. That is the next one you take, and y in the first case you have taken minimum of yi1, that is the first column, and this. Here you will take yi2 by yik for all I for which tie occurs in step 2. And if this minimum occurs for one value of I, say I equals t, then your at is the departing vector. So please note this one, then at is the departing vector. If the minimum occurs at more than one value of I, then I have to go to the next step. So compute like this way minimum of yil by yik for I equals 3, 4, n, like this. Means still you are getting at least one minimum, you have to continue the process for these values of I for which there is a tie in the ratio previous to present computation, until we get a unique non-negative minimum, which will indicate the departing vector. So basically I have to repeat the process until I am obtaining a unique minimum. Let us explain this one with example. First one, let us take it type 1 degeneracy, that is maximize z equals 3x1 plus 9x2 plus x3 subject to x1 plus 2x2 equals 0 and 2x1 plus x3 equals 1 and x1, x2, x3 equals to 0. Now here if you see all these variables, the constants are equality constants. So, as such I do not require any slack or surplus variables here. But earlier we have told if there is a equality to form a basis, if required you can add artificial variable also. But from here I can obtain, if I make x 2 as 0, x 1 will be 0 and x 3 will be 1. So, that solution basis you will get, your basis will be x 1 0 and x 3 equals 1, and which will form one unit vector 1 0 0 1. So, for this case I do not need any artificial variable over here, and the basis will be, in the basis the basic variables will be x 1 and x 3. So, I am writing here x 1 and x 3. So, therefore, this will be a 1 and a 3, values are 3, 9 and 1, coefficients of x 1, x 2 and x 3 are this. So, here it will be 3 and a 3 is 1, b value is 0 1. So, 1 2 0, 0 2 this is 1, 0 2, this is x 1 was absent. So, 0 2 1. Now, if you calculate zj minus cj value, you will find 0. Here it is 6 plus 2 8 minus 9. So, minus 1, and this value is 1 minus 1. Therefore, your entering vector will be x 2. Your entering vector is x 2, and what will be the this one? What will be this case? The ratio, the first ratio is 0 by 2, that is 0, second ratio is half. So, your departing variable is, in this case, is x 1. So, x 1 will go out and x 2 will enter. But if you have noted one thing, in the basis, for the basic variable the value is has 0 value. In B column, in the basic variable is 0 value. So, this is type 1 degeneracy, whatever we have told. Initially, we have seen that there is a basis, and in the basis value of the basic variable is taking as 0. So, degeneracy occurs, but in this case you do not have to bother anything, just proceed as usual to solve the normal problem. That is, you do the next iteration of the simplex algorithm, because you know what is the entering vector here and you know what is the outgoing vector here. So, for this case x 1 is the outgoing vector and x 2 is the entering vector. So, x 1 will be replaced by x 2 in the next table. So, if I form, let us form the next table now. In the next table, your x b will be then x 2 and x 3, because x 1 is replaced by x 2, you are having a 2 and a 3. C v values remains the same, that is 3, 9 and 1. So, x 2 is 9, this is 1. In the earlier one, your pivot element is 2, this is the pivot element. Therefore, your this I have to make as 1, and all other elements of this column I have to make as 0. So, I will make this, that is b value I am directly writing 0, half, 1 and 0. This will be 1, minus 1, 0 and 1. So, this one is 1 entering vector and this column is 0. Zj minus Cj value, if you calculate, it will become half, this will be 9 minus 9 0, this will be 1 minus 1 0. So, here if you see, your Zj minus Cj is greater than equals 0 for all j, and for the non-basic variable it is Zj minus Cj is greater than 0. It is here, that is this value for non-basic variable x 1, Zj minus Cj is greater than 0, whereas for basic variables x 2 and x 3, Zj minus Cj is greater than 0. So, you will obtain the unique optimal solution. In the basis, you have only two decision variables x1 and x2. So, your solution is x1 equals 0, x2 equals, from here it is 0 and x3 is equals to 1, and Z max, that is maximum value of Z from here, it is 1. This into 0 plus this into this. So, 1 into 1. So, value of Z max is 1 because Z is CB into B. So, Z max is equals to 1. So, basically if you see, although we had the degeneracy which we obtained in the initial table itself, we have checked there that the value of a basic variable is 0. So, in this case we do not have to bother anything, we proceed as usual and we will obtain the solution. Now, let us see the type 2 degeneracy. In the type 2 degeneracy, what happens? In the type 2 degeneracy, let us take an example. Maximize Z equals 5x1 plus 3x2, subject to x1 plus x2 less than equals 2, 5x1 plus 2x2 less than equals 10, 3x1 plus 8x2 less than equals 12. So, we have three inequalities of less than equals type. So, you have to introduce three slack variables, so that in standard form we can write down maximize Z equals 5x1 plus 3x2 subject to x1 plus x2 plus x3, this is equals 2, then 5x1 plus 2x2 plus x4, this is equals 10, and 3x1 plus 8x2 plus x5, this is equals 12. So, x3, x4 and x5, these are the basis, these are the slack variables which we have introduced, and xj greater than equals 0, where j equals 1 to 5. So, initial basic feasible solution will be, if I make x1 and x2 as 0, then x3 will be equals to 2, x4 equals 10 and x5 equals 12. So, initial basic feasible solution is x3 equals 2, x4 equals 10 and x5 equals 12. So, in the basis you are having three variables x3, x4 and x5. Here I am writing A3, A4 and A5. Obviously, in the objective function here the coefficient of artificial variables will be 0 only, plus 0 into x4 plus 0 into x5. So, your objective function is z equals 5x1 plus 3x2 plus 0 into x3 plus 0 into x4 plus 0 into x5. So, the Cj values are 5, 3, this and this. Your Cv values x3, x4, x5. So, these are zeros. B values are 2, 10 and 12. These are 1, 1, 1, 0, 2. This is 5, 2, 0, 1, 0, 5, 2, 0, 1, 0. Next one is 3, 8, 0, 0 and 1. So, again you calculate Zj minus Cj. If you calculate Zj minus Cj, this will be Cb into B, all are 0 minus 5. This will be minus 3, 0, 0, 0. So, most negative is this column, that is your x1 will be the entering vector. It is fine. Your x1 will be the entering vector in this case. So, now you have to calculate the ratio now. What will be the ratio? Ratio is 2 by 1, this is 2. Then it is 10 by 5, this is 2. And 12 by 3, this is 4. So the question comes now, here if you see the ratio, in more than one element has the same value in the ratio column, in both case it is 2. So that is a tie, and whenever there is a tie, if you go for next iteration by choosing any one of them, then degeneracy will occur. From the theorem we can tell that much. So whatever we have told, from there I can conclude that now I have to use that method, computational method, what we have told. According to the solution, as we have told, the next iteration must be, will give be degenerate. So let us assume that I am keeping it inside. Your A1 equals old A3, your A2 equals old A4 and A3 equals old A5. Means, as we have told, what I have to do? I have to recompute the ratios again, but before that I have to consider the first column as the first variable in the basis, that is now for x3 I will consider this is the column, for x4 I will consider this is the column, and for x5 I will consider this is the column. Means first three columns will now represent the three basic variables x3, x4 and x5, and that is the reason we are writing this one. A1 equals old A3, A2 equals old A4 and A3 equals old A5. Now I have to find out minimum of this one, minimum of, first I have to take yik, I1, then if you remember in the earlier degeneracy examples, it was yi1 by yik, yi1 by yik, where your value of I in kth order or k greater than 0 minimum occurs. Your entering vector is ak. So it is minimum of yi1 by yik. So I will write down is minimum of y11 divided by, what was that, yi1 by yik was there. So I will tell that minimum of this one, that is yi1 by yik. Next one will be y21 by yik. So what is yik? Yik will be the entering vector for this one. That is, I have to take the element 1 for the first case, and for the second case I have to take the element 5. In this case, so it is y1 and it is 5. That means y11 by y11 and this is y21. This is your 5. Now what is y11 now? What is your y11? Y11 is your x3, that is your this and 0. So therefore minimum of it will be equals to 1 by 1 comma 0 by 5. So this I am getting from the next two variables, because this has come here now, because we have told, we have interchanged x3, x4, x5 now coming at the first three columns. So since x3, x4, x5 are the first three columns, so y11 will be 1 and then y21 this will be 0. So we are taking 1 by 1 comma 0 by 5 and the value is this one. Therefore the new vector A2, it is occurring for y21 by this one old value. So new vector, that is basically old A4 will be the departing vector. Old A4 is the departing vector. So, is it clear? Little bit, let me explain once more. Since we have the ratio in two elements are same, there is a tie. So, once there is a tie, what I have to do? I have to compute the value of the new ratio. For that reason, what I will do? I am writing A1 equals old A3, A2 equals old A4, A3 equals old A5. And this table, I will visualize that x3, x4, x5 has come first, then x1, then x2. I may write down a new table basically where the columns will come as x3, x4, x5, then x1, then x2. This I am visualizing so that the elements of these will be now changing. Now the minimum is, this is the column yi, I will take the first one. So, y11 divided by y11, old value of y11 is 1. So, I have made it 1, then it is y21 by this one, this value here it is 5. So, it is 1 by 5. Now, what is y1? This y11 I will take from this new table. So, y11 means basically the value of x3, that is 1. So, I am writing 1 by 1 and in the second column it is 0. So, it is 0 by 5 and it is equals to 0. So, therefore, the minimum is occurring for the vector this one, this ratio is this, which corresponds to this vector A2. So, new vector A2, that is old vector A4 will be the departing variable. So, now here A4 is the departing variable. So, since A4 is the departing variable, your pivot element is this one. So, like this way you are just finding out whenever there is a tie. By this method, if you select which vector will be the departing variable. So, now let us go to the next column. In the next column, what happens? Your x4 will be replaced by x1. So, here it will come x3, x1 and x5. This is your A3, A1, A5. Your Cj values are 5, 3, 1, 2 and 3. So, here it will be 0, 5, A1 is 5, it is 0. Your these values will become now 0, 0, 3 by 5, 1, minus 1 by 5 and 0. The second row will be 2, 1, 2 by 5, 0, 1 by 5 and 0. Third one will be 0, 34 by 5. Sorry, this will be 6, this will be 0. Next one is 34 by 5, this is 34 by 5, 0, minus 3 by 5 and 1. If you calculate Zj minus Cj, it will become 0, minus 1, 0, 1, 0. So, that your entering vector is x2 now. So, I have to calculate the ratio. It will find that 0, 5, 30 by 34. So, the minimum is this one. Therefore, your departing vector is x3 and this is your pivot element. And there is no degeneracy till now. Sorry, there is a degeneracy because one of the basic variable is 0 over here. So, you are calculating this. In the next table, your x3 is going out, it will be replaced by x2. So, x2, x1, x5, 5, 3, 0, 0, 0 and CB is A2, A1, A5. These values are 3, 5 and 0. So, pivot element will be 1, all other elements of that column will be 0. I am writing directly 0, 0, 1, 5 by 3, minus 1 by 3 and 0. This will be 2, 1, 0, 2, 1, 0, minus 2 by 3, 1 by 3, 0, 6, 0, 0, minus 34 by 5, 5 by 3 and this is. So, if you calculate now, it will be Zj minus Cj is 0, 0, 5 by 3, 2 by 3 and this is 0. So, therefore, Zj minus Cj is greater than equals 0 for this case, and Zj minus Cj is greater than 0 for non-basic variables, that is here these two cases x3 and x4. Therefore, you will obtain the unique optimal solution. Your optimal solution is x1 equals 2, x2 equals 0 and your Z max from here it will be 5 into 10, that is 10. So, you are obtaining the optimum solution. So, whenever there is a tie, we have to find out the solution. Now, quickly let us see one thing, that is, if there is a tie, why we have told that redundant constraints. From the earlier problem, I can write down the constraints like this: x1 by 2, this x1 by 2 plus x2 by 5 equals 1, x1 by 4 plus x2 by 3 by 2, this is equals 1. If I draw something like this, there will be a line which will go through, this is a point 2, there will be another line which will go 2 and 2 like this, I am sorry, and this is, no, I have not drawn it correctly, this is not correct. There will be a point 2 here, there will be a point 4 here, here I need a point 3 by 2, 2 and there will be a point 5. So, there will be 3 by 2 and 4. So, one line will be like this, there will be one point which goes through 2, 2. So, this will be 2, 2 and there will be another one which goes through 5, 2. So, 5 and 2. So, if I draw like this, another point will be like this. So, this is the feasible region. So, this one, this is your 5x1 plus 2x2 is less than equals 10. And this one is redundant, because this is, if I do not write down this, then also your feasible region will remain same, the characteristics of the problem remain same. So, this constraint is the redundant constraint, and due to this redundant constraint only your degeneracy occurred in the problem. So, whenever there are redundant constraints, there will be degeneracy, or degeneracy can occur in two ways. One, it can be there is a 0 value of the basic variable in the initial step itself. Do not bother, proceed as usual. The other way degeneracy occurs whenever there is a tie, and if there is a tie, to resolve the tie, follow the procedure which we have discussed just now.